Vado. Vado? Ok. So welcome back. This is this is continuation of yesterday's discussion about finding the explanation of the mismatch between the predictions we have so far and the data in lab physics, and the place where we got was to finish and complete a discussion that explain us that this mismatch between the data and the theory cannot be due to an experimental effect. And the last attempt we did was to include this smearing of the energy of each individual particle in the bunch of particles that collide, which is coming from this probability distribution function f due to the beam energy spread, and I computed for you this formula. Then I also show you how to express it in terms of these other variables tau and y, right? In which essentially the cross section that we observe is the convolution. So it's the convolution between the beam energy spread of the two beams and the cross-section that corresponds to the collision that is truly happening. This formula is very trivial to derive. It's really just classical statistics, if you want, that has to do with the statistical composition of this beam of particles. So now, the true explanation of this problem of LEP is completely different, is theoretical, and it is the effect of QED radiation. So ultimately, it's the result of the emission of one extra photon in our process. So we have studied E plus E minus 2 FF bar, and we just considered the diagrams with the Z, but of course we say we can introduce also Z photon interference. But something that could happen in terms of Feynman diagrams, you could draw a diagram, for example, like this, in which now a photon is emitted. So there is a very last bit of experimental related information I must give you in order to explain why this is relevant. Okay, this is not the same process as before. There is also a photon now. So the cross section that is measured there, and so the one that we should try to reproduce theoretically, is called inclusive cross section. We already use this notion, maybe inclusive, when we discussed the problem of jets and radiation. Sorry, in QCD. So the hadronic cross section is an inclusive cross section. It sums over all hadrons, but this is a different notion. Let's consider, for example, E plus E minus 2 mu plus mu minus. They are leptons, right? Just to make clear, what we mean by inclusive is that it's the cross section for FF bar. That is to say, is a plus. We say like this, plus X. That is to say, experimentalists will check if there is a muon and an anti-muon. Okay, and if there is one, they will count this event. They will put it in that plot eventually. They will not check at all if there are photons in particular. So this in fact should be the cross section of FF bar plus the cross section of FF bar plus a photon, plus, if needed, right? If needed, maybe also the cross section with two photons. Okay. It's important to emphasize that whether or not, so that this photon, as we discussed, can be seen by the experiment, but not exactly always. In particular, if this photon comes very collinear to the beam line, there is no detector can be installed for principled reason, as we explained. And there is also no possibility to detect the photon if it has a very, very low energy. Again, for reasons of principle. So at least part of this photon emission cannot be resolved experimentally, okay? But none of them was considered in that measurement. Then one could do also measurement in which these photons were instead reconstructed to check the picture, but here we're focusing on this particular cross-section, so we don't have to worry. We can emit a photon, and we don't need in any direction, and this will be counted anyhow inside the observable that we're willing to reproduce, okay? So, first thing is to explain why this could be at all relevant, given that if you have studied quantum field theory, you have learned that when you insert new powers of couplings, and if you emit more bodies in the final state, there is a suppression. Okay, it's the same suppression that you have for loops. So this diagram here is in fact of the same order naively as the one in which instead you make a virtual loop. So it's a loop factor down with respect to the one without the photon. In fact, I'm referring here to the modulus square integrated over the phase space of the photon, which is normally, okay, of order E square over 16 pi square. E is the electromagnetic coupling, pi square, alpha over 4 pi, and this is a very small number of order 10 to the minus 3, okay? So why instead, so what's the catch here? So the point is that this estimate is very often violated, very badly, and so it's violated because of what is called an infrared enhancement. Which is like this. So let's consider our electron emitting a photon. And so it becomes a virtual electron. This is an electron propagator. And if the photon has a momentum k, and the electron has a momentum of p, this has, of course, momentum q equal to p minus k. So now, in the process we're interested in, then this electron will hit the other electron, form the Z boson, and do this diagram that we had over there. But let's consider, just in the drawing, let's say a more general possibility in which there is another, the other particle in the bin, for instance, the positron, that then hits this virtual electron and produces something. In our case, this part of the process is simply this diagram here. More in general, I will refer to it as the hard process. So now, the propagator of the fermion, as you all know, brings a factor of 1 over q squared minus the mass of the electron squared. And so let's compute this denominator, the denominator of this propagator, q squared minus me squared. We will use our usual light cone coordinates, so that we're going to write that the incoming electron momentum has a p plus component, which is E plus P3. It has a P minus component. So now I'm willing to take the finite electron mass into account. So it is mass of the electron squared divided by P plus. And then, of course, it has 0 transverse momentum, because it's the particle incoming from the beam. While for the photon momentum, I will use this parametrization. So I will call its plus component of the momentum, k plus, to be 1 minus x times p plus. Okay, this is just a change of variable. I find convenient to work with this variable x, right? So to measure the kappa plus momentum in terms of 1 minus x. Then it's going to have some transverse momentum, pt, in general. Okay, it's going to go fly away from the beam, and then it's going to have k minus equal to pt modulus square divided by kappa plus, which is 1 minus xp plus. Right. Right. Okay, let's make it big. So let us compute q square minus m square it's simple algebra that brings you the following result. There is minus pt modulus square divided by 1 minus x, minus 1 minus x times the mass of the electron squared. Okay. So what is the point? The point is that from this formula, we are going to see in a second that there are kinematical regions, so values of the pt and of x, of the emitted photon, for which this q square minus m electron square becomes extremely small. Okay, it becomes extremely small. It goes in the denominator of here, and so it produces an enhancement that is not counted in this formula here. Okay, this formula is generic. It's like if no big ratios of scales were present between here and there. While here, we can have a big ratio of scale if this virtuality, this is called virtuality, because as you see, is the difference between the q square of the virtual electron and the q square it would have if it would be a real particle rather than virtual. So that's called the virtuality. Which brings a low virtuality enhancement, or infrared enhancement. And this happens in this happens anytime you adjust PT and X to make this small. But it's convenient to distinguish two regions where there is this enhancement. One is the one in which the photon is soft. So for example, let's take PT of the photon to be of order epsilon, where epsilon is small, times P plus. And let's also take 1 minus x. Remember that 1 minus x is here in front of the K plus momentum of the photon. We want the photon to be soft, so let's take 1 over x to be of order epsilon as well. So you see that the virtuality is in fact low, and it's of order epsilon. Okay, so this gives order epsilon, q squared minus m squared, epsilon. But there is also another region, which is the collinear region. Which instead you take x to be of order 1, far from 1. So neither 0 nor 1, let's say 1/2, far from the streams, but distant, so distant at order 1 from the streams, though x is not difficult to check that for having a real photon needs to be belonging to 0 and 1. Okay? So the streams are 0 and 1, and when I say x of order 1, I mean somewhere in between this interval. And then instead I take PT to be small, let's say of order epsilon times P plus. So now the low virtuality has this term, which is PT squared divided by 1 minus x, which is of order epsilon square, right? It also has this term here, the one with the mass, that I cannot eliminate. I cannot take, so it doesn't matter how epsilon is, this term is always there, and it's always, well, negative, but it's always different from 0. So unlike in the case of the soft photon, which I can bring to exactly 0 energy because the photon is massless, so I cannot, in this collinear region, make this virtuality exactly equal to 0. But still, I can lower it a lot. Suppose I am at LEP, the typical scale of P plus here is of order of, I don't know, 100 GeV, while the electron mass, as you know, it's half mF, so it's much smaller than that. Okay, so I cannot have an infinite enhancement, but I can have a lot of enhancement. Now, of these two regions, the soft one is not going to be particularly interesting for us because Because the configuration I have in mind is that there is a very little small photon with small energy that is emitted. And so the initial momentum P of the electron, it's more or less the same as the momentum of the electron that's after the photon is emitted. That is to say, this virtual electron here will essentially have the same momentum as the real electron that was emitted, that was coming from the beam. That is to say, this one here, then is going to collide with the other positron, for instance, with the center of mass energy that is the one of LEP. Okay, there has been no change in the energy. Instead, if I go in the collinear region, then I am in this following situation. I do have a P plus at LEP. The energy, remember, is much above the mass of the electron. So P plus it's of the order of the energy, and it's much larger than the mass of the electron. Then I have this photon that is emitted with a PT that we said is much smaller than P plus, or which is the same, much smaller than the energy of the incoming electron. It has a kappa plus. So its momentum transverse to the beam is small, but its longitudinal momentum of the photon is large, because that is 1 minus x times p plus, okay, which is of order of e. Okay. Well, this means that this photon carries away, since x is far from 1, okay, and also far from 0, carries away a significant fraction of the energy that the initial particle had. Then simply this other one, okay, the momentum of this other one is dictated by momentum conservation. So it has a qt, it has a transverse momentum, which is minus pt, and of course it's much smaller than p plus and energy. And it has a q plus, which is x p plus. And that's why I found interesting to define kappa plus in terms of 1 minus x, such that when I subtract it, I get that the plus momentum of this virtual electron here is a significant fraction of the p plus of the initial electron. So what I'm saying in terms of energy is the same. So the energy associated to this q virtual particle momentum is essentially equal to x times ep. Again, equal because I am in the ultra-relativistic limit such that E and P plus are little different from each other. So EQ is X AP, which is equal to X, the center of mass energy, divided by 2. Okay? So I started from an electron which has exactly the center of mass energy, which is exactly on the center. So there is no beam energy spread considered here. There is only electrons, they're all equal. All the electrons that come have the same energy. But then somehow these ones here have a variable energy, which is a fraction, x, of the initial energy, right? And so this phenomenon that is occurring then is sort of telling us that now, when we perform the hard collision, it is like if this electron had lost some of its energy, right? And so it's something that starts looking very similar to this formula that I had over there for the beam energy spread. But still, here we are discussing about Feynman diagrams that, so we still have to work things out better to see how the explanation works. So one important thing I want to make clear here. So in order to study this diagram with photon emission, I want to do it in a general way, first of all, having in mind a generic hard process, not necessarily the one of LEP, because I want to emphasize an important property that one can show, which is that the Feynman amplitude for low virtuality, in our case, will be collinear. Photon emissions. So has a factorized and universal form. That means the following. Let's call M the matrix element, the scattering amplitude of the full process. Full being the one in which you do consider all diagrams correctly with the photon in the final state as well. So the amplitude for this. So this is equal, approximately, up to polynomial corrections in this low virtuality expansion parameter. It's equal to the product, that's why it's called factorized, the product between a splitting amplitude that we will briefly compute, quickly compute later, and essentially takes into account of this splitting, okay, of this electron becoming a sort of electron and the photon, times the amplitude for the hard process. That is to say, the amplitude for this part of the diagram down there. In this amplitude, very importantly, the electron that is incoming is going to be on shell. So it's going to have exactly 0 virtuality in this approximation. Okay. Times the propagator factor, the 1 over the virtuality, 1 over q square minus me square. That is the thing that eventually is responsible for the enhancement, and also for the reason why I'm interested in considering this region, because if I then compute the total cross-section, this region that is enhanced is the one that is going to contribute most to the final result. Universal, very important. Universal means that this splitting amplitude, okay, is the same no matter which process I'm considering here. Okay. So I compute it once for all, or once and for all, and then I can use it for any scattering process. The electron will always behave as derived from this formula with this specific splitting amplitude that now I will compute. Okay, so so there is an exercise, that guided exercise, again, on the webpage of GGI, that you can solve and cross-check the various steps that I'm going to outline for you here to derive this formula and to compute the splitting amplitude. And the steps are as follows. So first, you need to define a truly on-shell version of the Q momentum. So the Q momentum is P minus K. The Q momentum is equal to XP plus M electron square divided by, P plus minus P T square divided by kappa plus minus PT. And the Q bar momentum that I like to define is, of course, something that should be as close as possible to this Q momentum, but exactly on shell. So it's going to be XP plus ME square plus PT modulo square XP plus. This minus component, I'm fixing it knowing that the virtuality, so that the Q square must be exactly ME square, knowing the plus component and knowing that the transverse component is minus PT. Okay? And so you see that thanks to this definition, Q and Q bar are similar. So Q is equal to Q bar minus the Q square minus ME square divided by XP plus. So the low virtuality, right, expansion parameter, times a minus vector, that is to say 1. So 0, 1, 0, which is also the n minus light cone direction. Right. Then if we take the numerator of the propagator of the fermion, this is q slash plus me, and so we approximate it in the low virtuality limit as q bar slash plus me, and then q bar slash plus me, if you recall the completeness relation for spinor wave functions, for the u or the v spinors, can be written as in terms of the completeness relation, that is to say, sum over the helicities h of the wave function uh of some electron with q bar, right, for momentum, so u bar h of q bar. Okay. So then we take our diagram, which has this propagator here. We replace this approximation and this expansion, and we get sum over h of the splitting part of the diagram that multiplies u bar h of q bar, coming from here, times the UH, which was coming from the completeness relation, that multiplies the hard part of the diagram. Okay? So that's the Feynman rule multiplied for the wave function, and so it is the scattering the amplitude. This one also, right? We have the wave function for the annihilation of a spin 1/2 electron, okay, with helicity h, which then is attached to the Feynman diagram and becomes the amplitude. And so the result that we are finding, maybe it's better if I write it down there, is the full amplitude. It's not exactly like here, okay? Similar, but not exactly. So the full amplitude is the sum over the helicities of a splitting amplitude of helicity h times the hard amplitude, again with the helicity h label, times 1 over q square minus m electron square, which was the usual propagator enhancement. Okay, so mu s h just collects this part of the diagram, right, with the helicity that it has, while the hard amplitude, as you see now, is the on-shell amplitude that corresponds to an on-shell, okay, electron with momentum q bar hitting an electron and then producing whatever final state it is. Eh? Q bar is on shell. Okay? So Q is close to Q bar up to low virtuality corrections. Okay? And so that's why I can approximate things like this. Right. In fact, there is one further approximation that I could do before I delete here. So you see that the Q bar momentum, right, is it has a PT which is very small, right? Because we are in this, so we are in the region where x is of order 1 and the low virtuality is reached because PT is small. Okay. So now, when it enters inside this hard process, which is a scattering at large angle and large energy, this PT is negligible. Okay. So in fact, in the hard process, and only in the hard process, not in the splitting part, it is a good approximation to replace Q bar with Q bar collinear. That is to say, this thing in which I drop the PT, that is x p plus me square divided by p plus. Furthermore, the electron is very light, so this is something like, this is really effectively equivalent to xp plus 0, 0. That is to say, in the hard amplitude, so the hard scattering process, mh little h, is the Feynman amplitude for an incoming electron that has a energy, the p plus, but also the energy, because we are in the massless limit, which is x times ECM over 2, and, well, some helicity, L, helicity equal to h, E minus E plus going to FF bar. Okay, so it's the same scattering amplitude that we have computed last time, okay, in this case only with x1, right, that we have computed last time. So it's a scattering amplitude with an electron that in fact is moving a little bit lower energy than the beam. Only lower energy can be, because x goes from 0 to 1, so this one has always necessarily a bit less energy than the initial electron, cannot have more. Okay. So also from this blackboard here, you could immediately read the value, so how much it's the splitting amplitude, right? It's just this vertex, the QED vertex multiplied by the polarization vector. It's a spin 1/2 spin 1 amplitude, so it's very easy. So it's very similar. Its calculation is very similar to the one we saw for WDK and also then for the other calculations. So it's something like E U bar H of Q bar gamma mu U of H. No, sorry, U normal. So this is the wave function of the initial electron. And then there is the epsilon, the conjugate of the epsilon polarization vector for the photon, because this is a photon in the final state, not in the initial state like in the previous calculation. You're curious. And now we are there. So okay, just a technical note. I encourage you to do this calculation using these IF spinors, okay, because it's really much more simple. So, for example, the momentum, the spinor C plus, just to give you an example, is just ME over square root of x P plus 0, and the other one is also very simple. So if you use this basis, you will find this calculation very, very simple. No need of doing any approximation, it's just exact, and it gives you the splitting amplitude. And let's write them down. Let's write them down. Let's write them down here because they're quite big. No. Let's write them down here. So mu s for helicity. One last thing. For simplicity, okay, but only for simplicity, because Blackboard becomes too long, I'm going to take m of the electron equal to 0 now. This is not necessarily a good approximation, okay? Because now I'm considering the soft process, not the hard. In the hard process, it's a good approximation. Here, it's not necessarily a good approximation, but at the end, it works. I mean, it works pretty well in this case. So just to make your calculation easier. So this calculation becomes easier in two ways in this case. One, the formulas are essentially invariant, but one is that now for helicity, so okay, let's consider helicity plus 1/2 for the initial electron, and let's now write down the amplitude that we can have for the possible combination of helicities. So H equal to plus means that the virtual electron has helicity plus. And so let's take, for example, the photon plus. So E plus to gamma plus, E plus. This gives square root of 2 E P bar T. That's the complex combination, remember. So it's in fact modulus of PT times E to the minus I phi, the azimuth of the radiation, times 1 over root square x times 1 minus x. Okay? While if I take mu s plus, so the same helicity here, and I say I take, while if I take mu s minus, so the virtual particle has opposite helicity, E minus, gamma plus, E plus, right? I find something which is proportional to the mass of the electron, okay? And so it's going to be 0 in our calculation, okay? I will come back to your question, okay? Because, if I take instead mu s of, if I then now consider a plus, that goes into a photon, but now velocity minus, so I consider a quantum mechanically distinct process from this one, okay? This one is an electron plus and photon plus, and so this one has the true final states, external final states, and so they have to be, they cannot interfere from each other. E plus cannot interfere with E minus, so E plus gamma gamma minus, it can interfere because of the mismatch of the photon helicity, E minus. Everything depends on what I've written. So, sorry, mu plus, E plus to gamma minus, E plus, right? I get square root of 2 E pt, which is now is the same, so it's modulus of pt times e to the plus I phi times square root of x divided by 1 minus x. And again, the amplitude for the amplitude with h equal to h equal minus, okay, and so the one with here a minus will be proportional to m, and so we don't have it in our calculation. Right. So in our calculation, since we are setting the mass of the electron to 0, okay, we have only one non-vanishing amplitude for each h. That is to say, this one is different from 0, this one is 0, and the opposite way for the other helicities. And so we never see a non-trivial sum being done here, in fact. Okay? So for this specific way of, so for this specific approximation of doing the calculation, the result is the following. So we're going to get, well, I'm not going to write any detail, but it's going to be 1 over the flux factor. Then there's going to be some integral over the phase space of the final fermions, the integral over the angle, for instance, of the fermions. We could not do, we may decide not to do this. We may instead decide to have a calculation, and we will do it for the differential cross-section, differential in the FF bar pair. We could study the distributions of FF bar. Let's not do it for simplicity. But what instead we do absolutely have to do, since they're not observed, is the integral over the phase space of the photon that is emitted of the amplitude that now takes this simple factorized form, and there's not even the sum. And so it's just 1 over q square minus me square, that was coming from the propagator square because I'm doing the modulo square, and then I have, and then that formula over there, modulo square. So the integral over the phase space of the photon, it's d3 kappa over 2 pi cube 2e kappa. Or if you rewrite it in light cone coordinates, it becomes d kappa plus d3 transverse, sorry, d2 doubly differential volume of the transverse momentum divided by 2 pi cube times 2 kappa plus. And since kappa plus is 1 minus x p plus, so this becomes dx. So d kappa plus divided kappa plus just becomes dx, divided by 2 pi cube. There is a factor of 2. There is 1 minus x, and there is d2 pt. That maybe I can write it as pt modulo square dpt d phi. Right? The splitting amplitude clearly depends only on depends on x, right, and on pt. Depends on everything, even on phi. The hard amplitude, in the hard amplitude, we say that we can make this collinear approximation. Okay. So in first approximation, the hard amplitude, the initial electron in the hard amplitude, does not feel that there is any pt, right? So this does not depend on pt. Of course, it does depend on x, because x is effectively the energy of the particle that is getting in. So it does not depend on pt, but it depends on x. But of course, since it does not depend on pt, we can at least perform the integral over the phase space of the photon of the pt of the photon. We cannot perform the x integral instead over, so the integral over x. And so we're going to get the following form, the following structure. So we're going to have the integral in dx, that again we cannot do because the hard matrix element, okay, depends on x. The hard matrix element here, modulo square multiplied by the flux factors and whatever, will reproduce the cross section for the hard process, that is E minus E plus, where the E minus, I remind you, has energy E equal to x ACM over 2, going to FF bar. And then everything that remains outside, coming from the, let's say, the modulo square of the splitting amplitude integrated over pt of phi, does not depend on pt of phi because it has been integrated, just depends on x. And so I can call it Fe of x. Right? So in this formula, in this equation, I have exactly the same form that I had over there for one of the two beams, at least. So I have an integration over the fraction of energy that the electron is actually bringing. No? So technically, it's really like if the electron was not always having the same energy, but it had, from time to time, a fraction x of the energy that is variable, exactly like in the case of the beam energy spread. On the other hand, the physics, okay, a priori, was completely different. That is to say, here I'm just describing a statistical mixture of particles, of these 10 to the 11 particles that are in the bunch. I'm making a statistical description of those particles. Okay? But here, what I'm doing is just making a calculation that starts from a pure state. I just have one single electron with, by the way, fixed momentum, and it's a pure quantum mechanical state. There is not even a smithing, not even a wave function I've considered. So I have this pure state, and so I would, when I have a pure state, I compute the probability of something to happen as the out E modulo square, that you can also rewrite as E out E, okay? This out, you can view it as the quantum mechanical operator that you measure, right? It's the projector that is non-vanishing only when you get the right out state, right? So it's essentially so this is the quantum mechanical operator. If I have a pure state, the probability is the vacuum is expectation value, right, of this operator, right, of this operator, this filter that selects the right final state. But now, in the calculation, so by the effect of QED radiation, I end up with a formula that I would instead interpret by a density matrix. That is typically called rho, because I'm finding that the probability is a sort of a trace of rho times O, the same O up here, where the trace corresponds to the integral in dx, in fact, and the density matrix seems to be just a diagonal density matrix that corresponds to a statistical, purely statistical mixture, right? And to be differential only in this x. So d rho over dx, that will be the PDF or Parton distribution functions. Times, right? Same thing at here, but with an electron that has fraction of energy h. So times out E of x modulo square. Okay. In fact, the thing can become even more interesting than this in the case where you do not have this cancellation or this cancellation of the sum, in the case in which the sum over the elicities is non-trivial. In this case, we have only one elicity that contributes for each elicity of the external state in the massless limit. But for example, in the case of vector boson, effective vector bosons, even photon, Wulzer-Williams, there's plenty of other situations in which you can do a similar calculation, and you do have, in fact, mixed terms. That is to say, this sum remains non-trivial. When you take the modulo square, then you don't have a sum over the elicities, and so you don't have a diagonal density matrix rho, but you need to, but you do introduce a density matrix which is something like d rho over dx, but with indices h prime, which can be computed exactly in the same way. Okay. Actually, if you want to take the mass is different from 0, you will find a non-trivial density matrix, which then is used in calculation in formulas like integral dx. Then there is the sum over the elicities h prime of d rho h prime divided by dx. And then, of course, here, right, you're not going to have the simple cross-section like we have here, right? The simple cross-section for E plus E minus of a given elicity, summed and averaged, but you're going to have something like what is called a hard density matrix. So literally something like, I mean, it's flux factors, whatever, the same things that there are in the regular cross-section, but you do have okay? You have the hard matrix element times the alter matrix element with a different helicity, not the same, so it's not the modulo square, but it's something with two indices that then can be contracted with this one. It's a generalization of the cross-section, in fact. Interestingly, this type of situations give access to the quantum mechanical interference between the electron with helicity plus, the virtual electron with helicity plus, and a virtual electron with helicity minus. So these off-diagonal terms correspond to things that you can measure, right? That you could measure only if you could polarize your electrons, not as helicities plus or helicity minus. So yeah, there is a number of factors, right, in this definition, like the flux, there is the integral over the phase space. So pick up your definition in your mind of the cross-section, okay? And instead of taking the modulo square of one single helicity, you take MH times H prime star, and you construct a two-index tensor, which is the hard density scattering density matrix. If I have time, I will show you a very similar thing for the decay of an unstable particle that comes from a very simple, very similar consideration. It's interesting. One thing that I should comment, maybe even if it's too late, if you really integrate over the radiation fully, as we're doing here, there is a reason why this density matrix will always become diagonal. And that's helicity conservation that, for example, determines the azimuthal angle dependence of that. So the fact that this goes like e to the plus I phi, right? It's dictated by symmetries, and this will go like e to the 0. And so all these terms will have different dependencies on phi. That will make that if I really make the calculation of the fully inclusive cross-section on gamma, this will not show up. But if I start doing things like, for example, I measure the azimuth of the radiation, then I can access that interference. But okay, so this is, let's not go too far. Okay? So this is already interesting enough and instructive enough the fact that effectively we end up doing a statistical mixture type of calculation, even if what we wanted to do, actually what we are doing also, is the scattering of a pure state. So let's see if I can briefly complete the calculation of this PDF, Fe of x. So, okay, so first of all, the thing we have discussed so far can be used only to compute one part of this PDF, which is the real part. Let's say very quickly, is because we have not considered diagrams of the loop type. Okay, so I didn't want to write any loop. Of course, these diagrams are not particularly relevant for our problem because they don't change any energy, right? So the initial state, then the final state will have the same energy. So they're not the key ingredient, but if you want to do the full calculation, you also should include them. So this comes from d2pt, so modulus of pt, d modulus of pt, d phi divided by 2 pi cube twice 1 minus x. Then there is 1 over q square minus me square squared. Then there is in fact a factor that comes from the flux factor. That is to say, the fact that the flux factor that you have to put in the full cross-section is associated with the fact that the initial particles have energy ECM over 2. But when you want to reconstruct, to write this in terms of the sigma at cross-section, no, you do have to take into account that there is this has a different flux factor. So this 1 over q square minus me square that we already computed before, it's very simple, is 1 minus x squared divided by pt modulus to the fourth, pt. And then there is the splitting function squared, which are maybe still written up there on the blackboard, and this 2e square pt modulus square. So there is a contribution from the photon with helicity plus. There is a contribution from the photon of helicity minus that again you can read on that blackboard. Okay, we are of course summing over the helicity of the final photons. And let me take just the last step of this calculation to show you something important. So we have e square, well sorry, we have, what is this? Okay. E square over 4 pi square pi, some function of x, which is 1 plus x squared divided by 1 minus x. And then here, the important thing, that you have to make an integral, which is the integral in, let's write it as the integral in dpt modulus square, so differential of everything, divided by pt modulus square. So if you do this, you will realize soon that you get a logarithmic integral. Okay, dx over x. It's not x, but dpt square over dpt square. Of course, this integral diverges if we don't specify upper bounds for this integration. What's going to be the upper bound? Well, it's going to be something of the order of the maximal energy that the photon can possess. And that's going to be called q square. And in practice, we will set it to the maximum energy the photon would have, which is of the order of the energy of LEP, of order under GV. Okay, this we know how to set. The lower limit of integration is also important because this is a logarithmic integral. And to set this, we should recall, I told you that this virtuality q square minus me square cannot get really to 0 because there is the finite electron mass. Okay, so this means that if you lower pt, at some point you stop gaining in terms of singularity when pt is of order of the mass of the electron. And so clearly, for a first estimate of this integral, we just have to take a lower limit here, which is pt modulo square, because if we go below, we are not going to gain much, right? So the integral is effectively cut off at pt square. But again, if you do the full massive calculation, you will find the actual, you don't need any constraint. You can do the full integral, and you will find the result which is quite similar to the one that I get here. The result I get here, since it's a logarithmic integral, is of course a log. And so this is the fully final result, alpha over 2 pi times logarithm of q square divided by me square 1 plus x square divided by 1 minus x. Okay. And this is the PDF. You see, it depends also on another scale. So it depends not only on x, but it depends only on q square. In our lab calculation, this is a fixed number. This is 100 GV square. But in general, the PDF can be considered for arbitrary q scale, which is called the factorization scale. Okay? This is the maximal energy up to which you integrate on the radiation. Or if you want, below which you cannot resolve the radiation, or you decide not to resolve the radiation. Okay. I'm not going to discuss very well, or I'm going to discuss through a trick, the way in which I can deal with these virtual contributions. The way I'm going to do it is that, so the true actual PDF x q square is going to be the one we computed, right? Alpha over 2 pi 1 plus x square divided by minus x log of q square divided by me square, plus a contribution that comes from the loops. But I told you the loop do not change x. Okay? So you will find intuitive the idea that this contribution gives something which is proportional. It's a probability. I don't know why I'm calling it PV, but so virtual, because it's the virtual contribution, times the delta function of 1 minus x. So x equal to 1 means that the electron maintains the same energy. And this is the contribution that you get from loops. Now, you would expect that for this for this one being a probability density function, as I'm proposing you to interpret it, it should be normalized to 1, right? And in fact, it is. And in fact, there is a powerful theorem known as the KLN theorem that ensures that is associated with the cancellation of infrared enhancements, okay? That assures that the virtual corrections are precisely such that the integral, okay, of f(e) of x in the whole around range of x from 0 to 1 is equal to 1. Okay. Now, one can have caveats in the sense that what exactly is the PDF? Here, it's a result of a series of approximation. You may have different definitions of what a PDF is. So what in general one has to say is that this is 1 plus loop corrections, but small loop correction. So it's almost 1, okay? But in principle, you could define the PDF to be exactly normalized with 1, which is what the physics is telling you. What the theorem is saying is that, okay, fine, doesn't matter. Okay, it's 1. So at least at this order, for sure, what I did is correct. Essentially, I fixed this PV in such a way that the integral is 1. There is some subtlety related with regularization that if you look at the notebook, you can have fun. And this is what I find. Because what I'm going to do now is just to take this PDF in place of the beam energy spread, right? And do the calculation, the same calculation as yesterday, and compute the cross-section for the lab processes that we want to study. So this is called the initial state radiation, because the diagrams where the photon is attached to the initial state plays a bigger role, naively, but I will not explain you why it is naive. The formula that I'm going to use, well, I consider only the emission from the electron, but if I consider the emission for the positron as well, of course I get the same. And so I combine the two things. Here I'm denoting the PDF as this. So this is going to be called the PDF for the electron parton. Okay, parton is this. This is the parton. Okay, of the particle electron. Okay. Here, of course, I have a positron, and so I have a PDF for the positron in the positron. Well, positron parton in positron particle. That, however, comes out to be equal because of charge conjugation in QED. And here I have the partonic cross-section. Now you understand why I was resisting not to call it partonic cross-section yesterday when we were discussing the beam energy spread. This is the partonic cross-section because the cross-section for the collision of the two E plus E minus, let's say, after they emit the photon, so with momentum x1 and x2. And, yeah. Oh, sorry. So, yeah, some word on the trick that I did in order to make this calculation imposing the normalization, and here you have the result. So now you see that things works much better. So now we have, compared with this plot, so now we have in fact an asymmetric effect. Okay, more goes down on the left and up on the right, and it's qualitatively, or at least almost, I think I would say quantitatively, very much in agreement with this other plot. And also this one works pretty well. So this is the invariant mass distribution at fixed lab energy. It does not only have a peak, like you do have at the energy of the collider, but it also has a peak as the mass of the Z. And why? Well, because out of these PDFs, what essentially I'm doing is that I'm allowed to pick E plus E minus that have a center of mass energy, which is 90 GeV, and I told you that when E plus E minus have a center of mass energy of 90 GeV, there is this huge resonant peak of the cross-section. So the cross-section is much larger if E plus E minus were exactly on top of the Z peak than it would be if they had the, I don't know, 200 GeV energy, which is the energy of the initial collision. This is called radiative return. That is to say, the particles try to go back in energy, okay, to emit radiation until when they go to an energy where they can produce the resonance. Okay? And so in the final state, you observe that the two muons, for instance, in the final state, they were coming from a Z that is nearly on shell, and then it has a mass. They have an invariant mass of 90 GeV. Okay? Yes. We will comment on this. We will comment on this. Is this clear? Yeah. No, okay. So the dependence on the normalization scale goes, if the normalization scale goes in the alpha. You don't get any, so you don't get one more dependence on the normalization scale on the PDF. The PDF depends on the factorization scale. Factorization, not the normalization scale. So yeah, sure, but okay, what I'm saying here is that of course this factor needs to cancel this factor, so it also depends on the scale, right? What I'm doing here is just picking up this factor such as to be normalized. Now, if you're interested in the details, since there is a singularity, I cannot integrate this, we can discuss later, okay? But yeah, the logic is that I'm fixing this just to make it integrated to one. More questions? Sorry, say it again. No, as I say, the radiative correction to the process needs to be taken account separately from this. It's the loop, okay? It's literally this loop. Also, this loop you can study in a factorized universal manner, but of course it's a different study, and it brings a different result, which then fixes this coefficient. Okay, so let's try now to go faster, and especially what I want to do now is to try to generalize. I mean, we have seen a lot of calculations, and we addressed specific problems. Okay, this is a specific lab measurement. Oops, a specific lab measurement. It's even so it's just a fraction of what lab did, right? But the elements that I have introduced should allow me now to generalize and to discuss the whole of collider physics, at least telling you a few words about the LHC in a relatively short time and being relatively, hopefully, clear. So first, let me try to generalize this notion associated with this PDF of the electron into the electron. And here we have to make a distinction between particles, okay, and partons. So particles are literally, particles are the single particle states that we studied on the first day. Okay? So they have well-defined mathematical meaning and well-defined mathematical notion. And let's say the electron at lab or the positron is a particle. The proton at the LHC is a particle. The muon at the muon collider is a particle. What are partons? Partons are more mysterious objects. Okay? When we speak about partons, what we literally have in mind, I think I do have in mind, at least, is nearly on-shell lines of Feynman diagrams that can be treated as if they were on-shell particles in calculations. So that's why I wanted to emphasize that when I compute this, right, this diagram, I have here a particle, the electron that emits a particle, and here there is a parton, however. No, I don't want to call this one with the same name as the other particles, because in fact this was off-shell. This was a virtual quantum that somehow was described in a Feynman diagram, but in some sense is getting on-shell in the course of the calculation. What exactly are physical particles? I'm not sure. So this is the mathematical particles. Partons are not very well-defined objects, but it's true that whatever you want to understand about collider physics needs about speaking about the interplay between these two different things. We have seen, as explicitly as I could do this calculation, we have seen that particles contain partons and this is due to initial state radiation. Right. In particular, we have computed, and let me write it once again, this probability for an electron particle, E, for an electron particle, E, to contain an electron, but with the fraction x of the initial momentum. And factorization scale q squared, and this was once again alpha 2 pi log q squared me squared 1 plus x squared divided 1 minus x. Okay. We could have done another calculation that that would correspond to this type of processes in which I do have the electron, but then I emit a real electron. And then there is a photon that now is a parton, is off-shell, that that participates to the scattering process. For example, I could have this photon scattering with the positron and doing photon-positron, a simple process like this. And again, I could have done all the kinematics similar to what I did before, and I will find that there is an enhanced region in the collinear direction in which this photon has an energy, which is a fraction x of the center of mass energy divided by 2, or say, of the initial energy that this particle used to have. And so I could have obtained a different type of PDF. So the PDF of the photon, this time parton, content of the particle electron, which is alpha over 2 pi times the logarithm of q square over me square times 1 plus 1 minus x square divided, though, by x, which goes like 1 over x. Oh, I want to say that this is contain okay, this is a general thing, right? Particles contains many different species of particles, and the way in which this content is quote unquote distributed in this notion of PDF can be very different, for different type of partons. So inside the electron, we say we can have the electron, we can say we can have the photon, and this is supposed to be a plot of the PDF. So the one of the electron, we have also seen a plot before, is strongly peaked at x equal to 1. For the vast majority of the times, in fact, the electron parton, right, has the same energy as the electron particle. And the fact that we found a peak here, the fact that it was this huge enhancement here, as high as this one, is just due to the fact that the cross-section is huge because you are on the resonant peak. But in terms of luminosity, in terms of how many there are, it's just a tail, okay? It's just a tail, logarithmic tail. And this is the electron, in the electron PDF. If I study the photon PDF instead, you see that there is a singularity. We should discuss, well, we may need to discuss how to cancel it, but it doesn't matter. So there is a singularity here that makes that the vast majority of the photons which are inside the electron, that's also called the Wulzer-Williams approximation, that the vast majority of the photons which are in the electron, there are a lot of photons, okay, probability becomes peaked and very high, but they are at low x. So they bring a very small fraction of the momentum. So for instance, at LEP, I don't know, you may want to study photon-photon fusions processes producing, who knows, pi zero. I don't know what you will do with this, but there will be a lot of photon-photon scattering taking place at LEP by this PDF, diagrammatically represented like this. But if you plot their invariant mass, it will be in the very low region. So very, very low, much lower than these ones numbers that we're putting here. So here will be a lot of gamma-gamma collisions, while all the rest will be E plus E minus collisions with the structure that we have already seen in previous plots. Okay, some more comments also about more emissions or more corrections to this formula that we derived. So because after all, what we did was a simple 3-level calculation, and all the rest was interpretation to get a feeling of the result of these partons. But do we really need this interpretation? To some extent, well, I'm not sure of the answer, but there is one thing that you should take into account. We could do this 3-level calculation, and this was right, in the context of LEP, because this parameter, and I think it's the 4th time I write it down, alpha over 2 pi log of q square over me square, where q in the case of LEP is under GV. This parameter, so it's still small. There is the logarithm, which is this infrared enhancement I was telling you about with respect to the naive estimate alpha over 4 pi, right? So it's larger than alpha over 4 pi, but still alpha over 4 pi was so small that the logarithm has not yet made it to compensate. It's around 0.03. This parameter is called alpha log. So in general, if you have some infrared type of structure, some of theory in which there is a high scale and a low scale, the high scale being this q square factorization scale, you can estimate what's the importance of collinear emissions, so collinear like PDF, as this parameter, alpha 2 pi, well, you can put the 2 or not, as you like, log q square over me square. There is also another parameter that I should mention, which is alpha log square, okay? So alpha log square, which is alpha over 2 pi times the square of the logarithm of q square minus me square. This is also known as the Sudakov parameter. And this is not associated with PDF. It's not relevant for PDF, this parameter. It's associated with soft and collinear type of radiation that we will not discuss, and collinear. Okay. This is just to say that there is quite well understood theory that you can use to understand at least where you can do these perturbative calculations, like we did. So if alpha log is small, you can do just a 3-level calculation. If alpha log is large, or for other problem, if alpha log square is large, meaning larger than 1, then you are obliged to consider infinitely many diagrams to perform what is called a resummation. Which is to say, I mean, let's say in the case of LAP, it would mean that you have to include all possible loops and all possible also, as it was asked before, all possible emissions of different photons at any order. Of course, you cannot include truly the full diagram, but you include very smartly, include only the log enhanced part of these diagrams. And now, what I wanted to just to tell you, without entering in any of this, which is extremely exciting and cool, but I just wanted to tell you that these resummations, that not for all observables, but for many, there are relatively well-developed techniques to do, that we know how to do. When we know how to do them, I think, as far as I know at least, it's always because we do prove first or assume the factorized picture. That is to say, if I really want to make this resummation, in the vast majority of the case, I should take as a starting assumption the formula that the partonic formula, this parton versus parton, if you want, correspondence, the fact that the cross-section is the convolution of PDFs with R process is the starting point. Okay? This is to say, sometimes I can prove that, in fact, factorization and parton-particle duality is okay. Sometimes I cannot. But if I assume it, then it's where I can do these resummations and then, of course, compare them with the data. Right? And they work, and as we've seen, they are essential to compare. They're essential to compare with the data, even in this simple perturbative case. In the case of PDF, the resummation of this alpha log is particularly well known. Is due to Altarelli and Parisi. It is the Altarelli-Parisi evolution equation. That's how Italians call them. Others, they call it DGLAP, because apparently the result of Russian authors on top of Altarelli and Parisi that did this somewhere, right? And so this DGLAP is a technique that would allow me to go from this simple formula, from that simple formula from the PDF to a resummed PDF, which essentially would include, on top of what I did, would include also multiple emission of any possible number of photons. So what you were asking before. By the way, at the order in which you emit 2 photons, so at the second order in this alpha log, you also encounter the last PDF of the electron particle, which is the PDF of the anti-electron. This emerges from this electron, photon, which then becomes splitting into pair, becomes a positron parton. Okay? This is of order alpha square, it's alpha log squared. In our case, in lab energies, it's extremely small, it's 0.03 square, right? So that's why we ignore it. But, okay. By the way, there is no distinction this level from QD and QCD. And QCD, of course, alpha is much larger, and the log can also be much larger. And so all this is systematically something that you always have to the sum, okay, if you want to make a prediction, right? Good question. At some energies, so Q square larger than, yes, yes. At the same order can also become a muon. Yes, that's right. But okay, let me, yeah, okay, right. So it's a pity that I cannot tell you anything about DigiLab, but for example, the lab, the Peskin book, it's, I think it's pretty clear on this. Also the lectures by Michelangelo Mangano, I will point you out what they are about them, okay? So, right, so, some more comments. A priori, any species of particle contains all species of partons. So, for instance, if I start from a photon, okay, that can emit a real electron and, I don't know, an electron or a positron, right? Something like this. So, this, okay? What's going to be this? Is going to be the PDF of the electron or of the positron, depending on what you pick up, inside the photon particle. Okay. Now this is important. It's telling you that there is no reasonable way in which you can think to PDF as describing the content of objects. Because it's completely obvious that a photon cannot contain an electron because the electron is massive and the photon is massless, right? About the mass of, let's say, particles and partons, the criterion, so there is no connection between the mass of the partons and particles. As I say, the electron can be inside the photon. What you have to monitor instead is the factorization scale Q. That is to say, so in our calculation, everything was coming from this enhancement of the propagator. And if now I have here some parton of mass, some propagator with mass m, okay, then the virtuality becomes q squared minus m squared. And you can easily check by the previous calculation that this is bounded by 1 minus x m squared. That is to say, I cannot never go, okay, to lower virtuality than the mass that goes into this propagator. Okay, so for this to be an enhancement relative to all the rest of the diagrams, it would mean that this is getting small with respect to the hard scattering scale, right? In our case, was the lap scale, right? We say the electron mass is small, so there is no problem. In this type of processes, the electron leads to an enhancement because the virtuality is bounded, but is bounded by the mass of the electron that is small. But if the mass of the parton is much larger, right, than this scale, which is the factorization scale, then there is no way in which the parton can be inside the particle. So let's say the criterion is whether or not q squared is much larger than m squared. And so the true statement is that at some point, at some order, all possible, at some order, the PDF at factorization scale larger than the mass of any parton will start containing that parton as well. Just to give you, just for example, at lap energies, this was not happening, but if I am at 10 TeV muon collider energies, factorization scale of the order of TeV, let's say, or more, then I start having also things like this. I do have a nearly on-shell virtual W boson parton, which I can emit out of, for example, a muon, right? And so I do have, at these energies, in the PDF of the muon, I do have, in the content of the, so in the fake content of the muon, I also have a W boson inside the muon. But this, you can speak about this only when q squared is much larger than the mass of the W boson square. For masses below, there is no notion and no way and no reason to talk, of course, about the PDF of the W inside the muon. Okay, So the higher factorization scale, the more you access more, say, partonic, quote-unquote, content of objects, of things. The effect is W, the effect is Z, boson, similarly, that you have at high energies. So our next task will be to generalize all these notions in a discussion, brief discussion about the Large Hadron Collider, about QCD then. So let's try to list So we discussed everything in the electroweak context. Let's try to discuss briefly what's the difference in QCD. So the partons, okay, are the quarks and the gluons. There is no proton parton because there is no Feynman diagram or no theoretical description of QCD of hadron physics that contains a proton. So you will never speak about a proton particle. The particles, as you know very well, are instead the proton or the pion or the lambda. So let's say the stable baryons. Okay? And also this you know very well. There is no way to think of a quark or a gluon particle because of color confinement. So a minor, very minor difference between QED and electroweak physics is that parton and partons do not share the same name. We could speak about the electron, parton, and the electron particle. We give them the same name because there is a sort of correspondence. Maybe here there is not this correspondence. The reason is deep in the sense that it's color confinement that make that the degree of freedom that you use for a perturbative description at high energy that have nothing to do with the degree of freedom that corresponds somehow to the particles. The reason is deep, but the practical effects are limited. Okay, it's just a change of name. Of course, there are differences. So let's try to list them. If you study PDFs, of course, of QCD, they are not calculable. But this not because of some alpha log, as we were discussing before. They're not calculable because alpha is large. So explicitly, what you cannot calculate is the PDF of quarks, of course, now inside protons and so on, at a factorization scale, already at a factorization scale of order lambda infrared square. Okay. So I remind you that the alpha logs, right, become large when Q squared becomes large because the log becomes large, right? So for example, in electroweak physics, in QED, if you are at factorization scale that are of the order of the infrared scale of the masses, the calculation works, like at lab. It can be done perturbatively. Then you can use Attarelli-Parisi, get evolution, and so you get all the powers of this alpha L, which is becoming large when Q is becoming very large, but you know how to model it with this resummation. In the case of QCD, the problem is not doing Altarelli-Parisi. In fact, you can very precisely verify the Altarelli-Parisi evolution, digilab for the PDF, and go to Q squared scale, which is very, very high. Right? That's not the problem. That's okay. The problem, of course, is getting this thing in the very first place because alpha itself is large, while alpha is small. And so in electroweak, and so that's the issue. It's not a fully conceptual issue in the sense that, in principle, lattice calculation can compute the PDF from first principles, but concretely what they are done is, what we do for now is to measure this PDF somewhere else and then obtain the predictions. By the universality that we discussed before, you can measure the PDF in any process and then reuse them in any other process. And then you make what's called the PDF fit that gives you this type of plots here, in which you have now, in the case of a proton particle, its content of all possible things, up, down, anti-down, gluon, strange, charm, okay, charm, even charm, at a factorization scale, mu square of order 10 GV squared, so it will be, I think it's 3 GV, so it's 3 squared, right? GV, so very close to lambda QCD, this one here. And this is the evolution of the thing at energies of order lap energy type 10 to the 4, 10 to the 2 GV to the second power. Oh, notice one thing. So you see that the B bottom quark at this in this plot is present and is not present in this plot. And of course, it's because it's 5 GV. So it's above the factorization scale in this plot, which is done at around 3 GV. Okay, and so it's not a parton. It becomes a parton when you go to higher energy. And all this is Altarelli Parisi. It's matching, I mean, these calculations. Well, this is experimental input. Cioè, this is measurement. Then, okay, fine. What else? Yeah, another important thing. There are two types of PDFs, the valence, which are the ones that peak here, and the C PDF. So before I was talking to you about the photon PDF, the photon is definitely a C PDF because it's peaked at very small x, like these other ones. They're called C, I don't know why. But the gluon, the strange, the anti-up, the anti-down, they all peak at very small x. There are these valence quark up and down in particular, okay, the constituents, quote unquote, in some approach to the proton modeling that are very different, and they do instead peak at large x, but not at x equal to 1. There is no PDF here that has a huge peak at x equal to 1, like we saw instead for the PDF of the electron in the electron. And it's very important, because when we collide electrons, then we do have a lot of electron partons that bring the entire energy of the electron. While if we collide protons, in order to have some partons with x equal to 1, it's very, 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 very unlikely. Okay? And this is also why if you have to build a proton collider and you want to access a certain scale, okay, by your partonic collision, which are the ones that truly probe, if you want, short distance physics, then you have to build this partonic collider with the center of mass energy, S, which is much larger than, if you want, the interesting S at scale, collision scale, because the vast majority of times what you do is that you collide with a very small x, and so you can imagine 1/10 of the collision energy that to take out from proton colliders. Let's say 14 TeV LAC produces a lot of 1 TeV processes, 1 TeV collision, but of course there is not one single event will ever be observed to have 14 or even 13 TeV, or even 10, most likely. Okay. Okay, so I think I can, yeah, I have to stop here and see you tomorrow. So the acronym is the name of famous physicists, Lipatov, Gribov, but I don't remember them all in order. DGLAP is an equation. So maybe I can say a few words more about DGLAP. So DGLAP is an equation for the dependence of the PDF on Q. So you should imagine something like DF equal to some convolution of with some known kernel times the PDF itself. So it's a first order differential equation that allows you to compute